Okay. Next question is this: you have data. Can you tell that this can be modeled only by this circuit? And we saw that by and large it is not possible. Very simple case, yes, if you have only one capacitance, get the data, you can say, yeah, it can be modeled only by a capacitor. You have only one resistance, you get the data, let us say its noise is low level noise, you can say this can be modeled by a resistor. Resistance and capacitance in series, yes, you can model only by these two components. Anything which is complex, you will have multiple circuits which can give you the same result. And when you consider that you have experimental data with noise, you will definitely have questions on how good these fits are. It is possible to represent the data using unique set of numbers. If I write this in complex expression, in complex mathematics you can have what is called zeros and poles. If you write it as a complex expression and you write it as a fraction with function z here, another function of z, if you set this to 0, whatever you get are called zeros of this function, and if you set this to 0, depending on the type of function, you can get what is called singularity. Some of them are removable, some of them are called essential, some of them are called poles. I will not go into the complexities of those. Generally what we get here will be a polynomial here, and they will have what is called poles. And if we specify the data using zeros and poles, then it does not matter which circuit you use, all of them will give you the same result. Okay, that is proposed by Sadkowski. We write the impedance as a function of frequency, angular frequency. This example I will write it as R5 in series with this pair of R6 and C6. So, I can get the impedance of this R6 and C6 parallel element and write this as a function of j omega. If I set the numerator to 0, I will get a value for this. When would the numerator go to 0? I can get the value at what frequency would the numerator go to 0? What frequency would the denominator go to 0? So, I can say this omega numerator is going to 0. So, the R5 plus R6 divided by this number with a negative sign, that is a 0. I can say this is the pole. So, of course, I have given the numbers here, but if you give values for resistance saying this is 10 ohm, this is 100 ohm, this is 20 microfarad, you will get one value here for omega, another value here. This happens to be an imaginary number, in general it can be a complex number. We will say for this system, this is the 0 and this is the pole. Then even if you represent by another combination of resistance and capacitance, they would also have the same 0 and same pole. So, if you want to specify that this is the spectrum I got and these are the zeros and poles, then you can tell this is the unique way of representing it. Problem with this is it is not easy to assign physical meaning to the zeros and poles, meaning I can't tell the 0 has moved by this, therefore, this adsorption is stronger or adsorption surface coverage is more or the film is thicker. With electrical circuit, to some level it is possible. So, although we know there is a unique way to represent it, you do not find that used commonly because of harder physical interpretation.
Have the same 0 pole and another system has same 0 pole, then they are equivalent?
No, once they have the same 0 and pole, that means the spectrum that are coming from there are equivalent. It does not necessarily mean the system are equivalent. Okay. If I have a circuit made out of the resistor and capacitor as given in the top circuit, you make another circuit as given in the second one, both of them will give you the same impedance at any frequency, as long as we have the equivalent values here, right. Now, from the data you can't tell which circuit is the one that is generating it, okay. But you might come up with the top circuit, somebody else might come up with the bottom circuit, and then each one may claim this is the correct circuit. Whereas, if you represent it as zeros and pole, both of you will get the same number. It is easy to look at it and say, look, both of them have the same number, it is the identical result. It does not necessarily mean the generating circuit is identical or generating systems are identical. It just means there is no ambiguity in figuring out which is a better representation, because we do not ask that question. Now, there are many software that are available to get these values. Commercial software usually that comes with the instruments are there. Publicly you can get a software from Ross McDonald's website. you can get a Z view, I think it is a demo, I am not very sure. You can get another software called multiple AAS program. You can get a demo version of a commercial software called Zimfin. That is what we usually use, not the demo version, we bought it with the instrument. You have something called AAS spectrum analyzer, you have a MATLAB based program, ZFIT, I think there is also one called ZFIT GUI. You can go to the website of Professor Biocomp and get equivalent circuit. They use in general either simplex or complex nonlinear square called LEVM algorithm. Some of them say they use the combination, they will use one to come to a good initial guess and then the second one to go to the actual optimal. As long as your spectra is simple, I think all of them work. When spectra is complex, you will have to get the initial values correctly and you will have to do some work to get those. Okay. Some level, knowing which circuits are distinguishable, which circuits are equivalent, that helps. Some level, knowing what to expect at high frequency limit and what to expect at the low frequency limit helps us simplify and get some initial guesses correctly. Physically, how would you go about? You have to know something about the system. These are some examples proposed in literature. You have a metal electrode covered by a non-porous insulating film and to the right of it is electrolyte. We do not expect any current to pass through because the insulating film is just going to block everything. You can represent this by one capacitor, another capacitor in series with a solution resistance. When you get this, all that you get here in the data can be modeled by a capacitance and a resistance in series, because these two you can't add them, but you can take the inverse and add them, and what you get is the inverse of the effective capacitance. Now, if you know that you are coating a film of certain thickness and you are measuring the spectrum, you coat with a different thickness, you measure the spectrum, you will get a different value here. Now, you have to take this and say I am going to interpret that as sum of two capacitances, one of them is fixed, another one is changing, and hopefully you will have another method to measure the thickness. Then you can come up with an idea of what is happening here to estimate or check whether this is giving you the correct result. You can sort of use it as a validation. Now, in general, if I do not know that this CF and CDL are arranged like this and CDL remains the same, in general if you give me two spectrum, I can't from that tell you what the value of CF and CDL are. I have to know that these are coming from a system like this and the CDL is the same or hopefully it is the same between these two experiments. Therefore, any variation there I can assign it to CF. Otherwise, all that I can say is this can be modeled by a resistance in series with a capacitance, that is all. If you have a porous film which is insulating and the electrolyte is there, that means some liquid passes through this and reaction can happen here. You will have double layer along with reaction and Warburg impedance for mass transfer effect. Porous film means it is not really flowing freely, and concentration of the reactants and products here are not the same as the concentration of the reactant products at the bulk material. Now, this is in parallel with film capacitance. Also, because electrolyte has to go through this, there is some resistance associated with this. So, a circuit given by this RF and CF in combination with CDL and RT and W with solution resistance for the remaining bulk, you can use that. But basically you have to visualize how would this behave and then use a circuit. If we say I have a conducting film, it is not porous, it may be semiconducting film, it may be a conducting film, it is not porous, reaction happens only here, there is no penetration of this electrolyte into this film. I can model the left side conducting film with the resistance and capacitance, the resistance will be low here and that is in series with the reaction that is happening here, double layer here, charge transfer resistance, Warburg impedance and so on. Now, if you count this, you have similar number of resistance and capacitance here. I can take this is resistance, let us say for whatever reason the Warburg impedance is not significant. So, I can say capacitance in resistance and another resistance. I can model this, replace this with a resistance in parallel with a capacitance and resistor. So, I have to know beforehand what am I looking at, what circuit can physically represent the system. You have to make a guess and then model this.
So, every time reaction will be represented as resistance or something else?
No, this is assuming the reaction can be represented by a simple resistance. So, next after this I want to show you how we can get the impedance of a reaction. In a very simple case, we will show the impedance of a reaction can be represented by a simple resistance. In more complex case, we will see how it can be represented.
What is W?
W here represents what is called Warburg. It is the name of a person who first came up with an expression for mass transfer based impedance. Okay, so, this is called Warburg impedance. Now, that also we will discuss, but then that will happen after we discuss the reactions. So, maybe a few weeks from now. If we take impedance spectra, we have seen some examples. We have seen something which looks like this, we have seen something which looks like this, we have seen something which looks like this. Variety of things. Now, high frequency limit. This is going to be high frequency and this is the low frequency. High frequency, low frequency. Here it's a starting point is high frequency, ending point is the low frequency. High frequency limit is usually the solution resistance. Okay. So, we saw this, you have a resistor, you have a capacitor, you may have a reaction with a complex impedance, and that is often called Faradaic impedance in honor of Michael Faraday. So, any electrochemical reaction, we are assuming there is no film, there is no mass transfer issue. In general, if it is kinetic limited, it can be represented by this. Okay. When you go to very high frequency, the impedance of the capacitor will be 0, close to 0, because we know it is going to be given by 1 by j omega c. That means, all the current will pass through this and not much current will pass through this. So, we will say most of the current passes through this, we will say all the current passes through this. That means, only resistance offered is here. So, solution resistance will be the high frequency impedance. If we go to very low frequency, capacitor will not allow much current to go through, because omega tends to 0, 1 by omega tends to infinity. So, this looks like an open circuit, all the current will go through only the Faraday process or the electrochemical reaction, and of course, the solution resistance. So, low frequency impedance is going to be solution resistance plus a resistance which is called polarization resistance. Polarization resistance is basically take the Faradaic impedance and at the limit of omega tending to 0, the value of the Faradaic impedance is called polarization resistance. That essentially means I have a surface, I want to change the polarity, meaning I want to move it from whatever voltage it is in, I want to make it little higher or little lower. Correspondingly, how much will be the change in current? Okay. I want to do it slowly. So, that ratio of change in potential to change in current, when we change it very slowly from whatever value we are originally at, that is called polarization resistance. So, if I change the potential, it is possible that more species may adsorb on this, less species may adsorb on it, all those processes are taken into account. Overall, what is the change in current? That is given by this omega tending to 0 Zf. Faradaic impedance is basically the impedance offered by electrochemical reactions. So, this example we have a solution. So, the resistance offered by solution is called R solution. Resistance offered by the capacitance, even if there is no reaction, AC current can pass through this, that is double layer impedance. Resistance offered by the reaction, that is Faradaic impedance. So, together we measure the total impedance. All that we can measure is the total impedance. But we want to separate out or deconvolute and say this component I want to assign to solution, this component is coming from double layer, this component is coming because of reaction. Usually we want to understand what is happening in the reaction, that is why we do the impedance spectra, but then we can't get the impedance spectra of the reactions alone, we will get it for the system. So, this is first step of separating them out. Okay. Now, I know I can get the polarization resistance if I know the Faradaic impedance, and this if I measure it will be the lowest value, but the lowest value here is not going to be polarization resistance, it is going to be sum of solution resistance and polarization resistance, because the circuit tells us total impedance that we measure between these 2 points, it has to go through solution resistance, it has to go through double layer capacitance also, but because omega is close to 0, I know that I can neglect this part and I can say it is going here and here. So, what we measure as the low frequency impedance, and it has to settle at this value. If I measure up to this, I can't call this as a polarization resistance. I have to see where it settles. That means, I go to lower and lower frequency, it remains more or less at the same level, then that is polarization resistance. Well, actually that is not the polarization resistance, that is a low frequency impedance, and that is the sum of polarization resistance and solution resistance. If our solution is very small, you can say approximately low frequency impedance is the polarization resistance. So, sometimes in publications or in books you will see you measure the impedance, the low frequency limit is the polarization resistance, they are implicitly neglecting the solution resistance. So, do not take a point like this and call this as polarization resistance if this value is not close to 0, that is first. Second, there is a definition of another term called charge transfer resistance. In reactions, I had to explain it a little, so just be patient for a minute. You have rate constant K, you can have other terms, concentrations of species K1, K minus 1, you can have other intermediates in a more complex reaction. Whenever we change the potential, the rate constant changes and it is supposed to change exponentially. And similar way minus 1 minus alpha, etcetera. There are different ways of representing this. For forward reaction and reverse reaction, they are going to have exponential relationship, but in one case it will increase, in other case it will decrease. Now, if I change the frequency very fast, okay, if you remember the circuit, this is the solution resistance, this is the capacitance, and this is the impedance offered by the Faradaic process. If I change the perturbation or the sinusoidal potential very fast, omega tending to infinity, all current will go through this, correct, because this offers almost 0 impedance. Go through this and I will see only R solution. But let us say that I can separate this out, I want to find out what happens to this Faradaic impedance when omega tends to infinity. When omega tends to infinity, this Faradaic impedance will tend towards a resistance, sometimes it is denoted as RT, charge transfer resistance, sometimes it is denoted as RCT, it will go to a resistance. For a given system, if you go to high frequency, it will tend towards a resistance value. Okay. That resistance value basically depends on what happens to this K1, K minus 1 as we change the potential. Concentration at the surface, now visualize this, you have a electrode on this side, you have a solution here. Let us say mass transfer is also playing a role. Now, if I increase the potential here, one of the species will get consumed, another species will get produced. So, whichever gets produced will diffuse out, whichever is consumed it will diffuse in, because concentration is decreasing now. If I increase and decrease the potential very fast, example 100 kilohertz, within 1 second it goes 10 power 5 times. Species will not diffuse in and out that fast, it cannot cope up with this speed, but the rate constant will still go up and down. So, effectively everything else will remain same, only the rate constant will change. Even a species adsorbs or desorbs, it cannot adsorb and desorb that fast, and at the limit of infinite frequency it definitely will not cope up with this, whereas the rate constant, it is directly related to the potential. So, whenever we increase the potential, the rate constant also will increase or decrease. So, Faradaic impedance, when you apply a slow change, the change in potential and change in current, that ratio is polarization resistance. Faradaic impedance, when you apply a fast change, it will also tend toward a simple resistance, and that is charge transfer resistance. Now, if the electrochemical process is very simple, then this Faradaic impedance I can represent it using a simple resistance. So, at any frequency it will give me the same resistance. Therefore, in this particular case, charge transfer resistance and polarization resistance, they will be the same, because 0, 10, 20, 100, 1000, million, all frequencies I get only one resistance. Therefore, the upper limit is the same number, lower limit is the same number. This sometimes causes confusion. People sometimes represent a system and then say the low frequency limit is charge transfer resistance, or high frequency limit they will take it as a polarization resistance. It is not correct. If you have an impedance spectrum, as an example I will give you one case. Spectrum looks like this, it may look like this, it may look like this, and we have taken enough number of points, we know it settles here. It is not that it is going to go in a different fashion if you go to lower frequency. Now, this is RP plus R solution. If it is negligible, I can say it is RP. This extension of this where it settles here, that is going to be RT from this point. That means this value is RT plus R solution, but if the solution resistance is negligible, it is going to be RT. So, if the solution resistance is significant, this point, this impedance is RT plus R solution, this impedance is RP plus R solution. Charge transfer resistance, you can get it only via impedance measurement, you will not get it using other techniques such as linear polarization or potential dynamic polarization which is often analyzed using a particular type of analysis called Tafel analysis or Tafel extrapolation. They will give you RP and they also assume that solution resistance is negligible. All that they give you is actually limit omega tending to 0 Z total, that is all you get from linear polarization and Tafel extrapolation. If solution resistance is 0, that will become equal to limit omega tending to 0 ZF, and that is going to be only RP. If you want to get RT, you have to get it via impedance measurement, and you should clearly separate out polarization resistance and charge transfer resistance. With very few cases they will be the same, meaning the values will be the same, the definition is still different. It may so happen that the value is the same, meaning I can get 100 ohm. For that system, charge transfer resistance is 100 ohm or 100 ohm centimeter square, polarization resistance is also 100 ohm centimeter square. It does not mean the definition of charge transfer resistance and polarization resistance are the same.
So, but it's not possible practically,
It is quite possible. This is all the spectrum. Okay, this is solution resistance. Low frequency impedance settles here. Solution resistance is, let us say, 0. Now, if I go to this and say I want to know this impedance at low frequency, I want to know this impedance at high frequency, the value is the same. I will give another example if that makes it a little harder. Comes and settles here, you will get the same number, but it does not mean the meaning of polarization resistance and charge, you should not use them interchangeably. Now, previously we had taken some examples. I want to look at the numbers again. Solution resistance is some value 10 ohm, 0 ohm, whatever it is. Double layer capacitance is 10 power minus 5 farad, 5 centimeter, this is a reasonable number. And this is for a circuit which looked like this. We got R1 and this is modeled by a circuit. We got solution resistance, double layer capacitance. We put one resistance here. We put a resistance and a capacitance. We put a resistance and inductance, saying okay, this is high frequency, this I will use inductance, this I will use a capacitor. That means first part can be modeled by a capacitance and resistance, this is what normally we would use. Solution resistance may be there, so I will put a resistance here. This loop is inductive loop, therefore I will use a resistance and inductance. This loop is a capacitive loop, I will use a resistance and capacitance. Now, if you just use this circuit normally and then do not realize that this number has to be negative, you will have a problem. You will not be able to fit it correctly. It will fit almost, but if you measure the parameters, you will see that uncertainty in the parameter is very high, and you will see that if you use equivalent circuit with capacitors and resistor instead of inductor, you can get, and allowing for negative values, you can get better fit. And you can again use the degenerate circuit to get back to this level, you get a negative value for this. This capacitance comes as 1.3 10 minus 2 farad, that is 130 millifarad or 130, 13 millifarad. Resistance is okay, 15 ohms. You get the inductance as 0.63 Henry, which is actually a large inductance. Now, we can't really explain the high capacitance value here, it does not mean we can store a lot of energy here. What it means is the circuit, this spectrum can be generated by a circuit like this. It does not mean the electrochemical reaction has the capacity to store this much. It does not mean it has a effective inductance of this. It does not mean there is going to be any magnetic field associated with this. And you have a negative resistance, it does not mean current will go in the opposite direction if you apply potential in one direction. So, we have difficulty in explaining this from the circuit. We can fit it to a circuit, that is good, but what do we make out of these numbers? Okay, I can't make much out of these numbers, but just like we look at the reference electrode, we say that I can't measure the potential of a single electrode, I can measure the potential of these two electrodes together, and knowing that this is fixed, any change that I apply, I think it happen only here, therefore I can interpret the result. Likewise, maybe I do not really understand this, but if I change the system a little, these values will change a little. Can I interpret that? That is better than not knowing anything about this. Even that has problem. Okay. First, when you fit the data, I just made up these numbers. You get a data, you fit it to this circuit, you get system like this. Another software will tell you this will move up and that will come down. Another software will tell you this is 200 ohm 300 microfarad and this is 100 ohm 1000 microfarad. They are the same. Let us say you change something here, maybe you change the concentration, you change the DC offset, you get a different spectrum. Now, you can fit it to this circuit. We use only one software, we do not worry about this. Now, I have a question, has this moved from 100 to 150 and this has decreased from 200 to 180, right. Now, when the resistance goes from 100 ohm to 150 ohm, the capacitance decreases. I had chosen it like this many times. If you take a given system and alter something, if one of the resistance goes up, the associated capacitor will go down in magnitude. Okay. You may or may not know this, it is okay. Right now, let us just say that 100 ohms might have changed to 150, that means it has increased here and 200 has decreased here and associated capacitance have varied in some fashion. That is a possibility. It is also possible that 100 has become 180, it has increased a lot, and 200 has become 150, decreased a lot. It is moving in the same direction, but it has moved much more than what you would interpret if you are taking the first resistance goes to the first resistance here, and you never know which one is going to be the top or bottom. it is not easy to interpret electrical circuits, even the changes in the circuit when you have a complex spectrum. When you have very simple spectrum, yes, if you have a spectrum, then you move the reference electrode a little bit more, solution resistance will change, that change you can interpret it. You have a reaction, you think by adding some chemical it is adsorbed and blocked, that everything remains the same, the spectrum pattern remains the same, just the values are changing. Those cases you can interpret it, hopefully the physical interpretation of this resistance and capacitance will be meaningful, but in general when you have complex reaction it is not possible.